In this video I will talk about an RL circuit, and when I say RL I refer to the resistor with resistance R and the inductor with inductance L. Now we are familiar with resistors, we're familiar with the power source. In this example I also have a power source, and the purpose of what does the inductor do in a circuit? An inductor will resist any change that you want to make. I want to remind you, if you have the self-inductance, you can find the induced EMF in an inductor by using minus L di over dt. Now, and remember, this is the current and the induced EMF in the same circuit. So anytime you change the current across the inductor, you will get an induced EMF that opposes that change. This is what inductors do. They oppose the change. So what I'm going to do here, I will have at t equals 0, I will close the switch, and thinking in terms of the electric fields now. The electric field inside the battery points to the right. Once I close the switch, I know that the conventional current will flow this way, and the electric field here will point down. Now, because the inductor, okay, if this was if you see the electric field in the battery points to the right. Now, because the inductor opposes the effect of the battery, the electric field inside the inductor will point upwards in that direction. Now I'm gonna follow. I'm gonna apply Kirchhoff's loop rule, where delta V around the loop is 0. This is the loop I'm gonna follow, and this means I will have VB minus VA plus VC minus VD plus VE minus VD plus VF minus VE, and then after F, I think I forgot something. After F, I'm going back to A. Yeah, so I think I forgot I need to add VC minus VB. Alright, I forgot that term over here. Now, because I am using, I'm assuming I have ideal wires, there is little potential difference across my ideal wires. When I go from A to B, I don't have any potential difference. From B to C I do, from C to D I don't, then from E to F also. Now, thinking in terms of the signs, because I'm going from A to B, from B to C, I'm moving upwards in the same direction as the electric field. This will need to be a negative number. And across the resistor, I'm going downwards in the same direction as E. This will need to be a negative number. Then I'm going against the electric field from F to A. This will need to be a positive number. So from B to C, I am moving across the resistor, and the induced EMF that I have will be minus L di dt. Now for the resistor, it needs to be a negative number. It's an ohmic resistor, so I have minus IR. And then when I'm going from one side of the battery to the other one, I just have plus EMF is equal to 0. Now here I have a differential equation where the current is my unknown. Okay, I do know that at t equals 0, the current starts at 0. Okay, I know that I don't have any. Now I need to solve this differential equation and to find the current that flows in the circuit. Now I will rewrite this differential equation IR plus EMF equals 0. I will show you how we can solve this differential equation. I will keep minus L di over dt on the left side. I'm going to move IR minus EMF on the right side. Now from here I will have di. I will divide with IR minus EMF. And the reason why I do this, I want to separate the left from the right and the two variables. I have the current and the time, and everything about the current is going to go to the left. Everything about time is going to go to the right. And this is going to be minus 1 over L times dt. So minus 1 over L dt IR minus EMF. And now that I have those two sides, I will go, let's say, okay, I'm gonna put primes here. So this is gonna go from 0 to t, and this is gonna go, my current will go from 0 to I. Now here I do have in the denominator I have I prime r minus EMF. I do need to, I know that this integral is gonna give me a natural log of this, but I also need to remember that my variable of integration I prime is multiplied with a resistance R. Now this will give me the natural log I prime will be IR minus EMF minus the natural log when I prime is 0. This will just give me the minus EMF. And as I said, I do need to remember that because I'm multiplying the variable I prime with an R, I need the derivative of this will give me an R in the numerator, which to get rid of it, I need to do an R in the denominator. And this is equal to essentially minus 1 over L times T. I can move R to the other side and I can simplify things a little bit. This will give me IR minus EMF divided with a minus EMF. This is the minus R over L times time. And I can get rid of the natural log. E to the minus R L T. Now I don't really like having this here. I will rewrite it. So next step, IR minus EMF. I will bring, first of all, I'm gonna bring this to the other side. So it will be minus EMF times E. Now the way that I like to write this is minus T divided by L over R. Okay, and this is L over R is what we call a time constant for this RL circuit. This is a little tough. L over R, that's your time constant for the RC circuit. So we had RC for the time constant. Here for RL circuits it's L over R. This is the time constant. So I can write this as minus EMF times E to the minus T divided by my time constant. And now I can move Okay, I can move this term to the other side. So it will be IR equals EMF. And how about I take it out as a common factor? So this minus becomes plus, and I have a minus E to the minus T divided by the time constant. And then if I divide with R, I have EMF divided by R 1 minus E to the minus time over the time constant. This is the expression for the current, and this shows you that the current in this circuit is a function of time, and the time constant shows you how much time you need to wait until the current gets the value that it would have if you did not have the inductor in the circuit. So I know, okay, if I do, say this is time, this is time, this is the current that's flowing in the circuit, this is the zero. If there was no inductor in the circuit, okay, with this line I'm gonna show you the EMF over R. This is how much current I would have flowing in the circuit even from the beginning if I did not have the inductor. Remember, the inductor's role in a circuit is to oppose any change that you want to make. And what I want in this circuit, when I close the switch, I want to go from 0 to EMF over R. The inductor will not let me do that. Instead, what this function here shows you is that the inductor is going to let you approach that. And in particular, the time that it takes, say this is tough, this is too tough, and so on. So if your time constant is on the order of a second, let's say, then it's going to take you a few seconds until your circuit reaches EMF over R for the current. If your time constant is on the order of 10 minutes, then it's going to take you more like half an hour for the circuit to approach the current of EMF over R. So the time constant is a very useful quantity. Once you know it, then you get a feeling for how much time things will take in your circuit. Now, in this particular example that I did, I have an inductor, a resistor, and the power source, and I'm closing the switch, so I want to have a current flowing in the circuit. You can think of, let's go back. You can think of a circuit where somehow you do have a current, somehow you're able to have a current flowing in the circuit, and then if you remove the power source, let's say you somehow bring a wire and you connect point B with point E, then you're going to bypass the power source. Anyway, if you remove the power source, then the change that you want to make in that case is you want to decrease the current and make it go down to 0. Now, what the inductor will do though, once you remove the power source, the inductor will try to oppose that change. And what that means, the inductor will try, it will not succeed, but it will try, and it will maintain some current flowing through the resistor, even when you take the power source out of the circuit. And that means, in that case, when you remove your power source, the current will not go down to 0 immediately. it will take some time for the current to approach zero in an RL circuit. That's because the inductor is trying to oppose the change. Now, how much time is that? Again, that depends on the time constant. If you know the resistance and you know the inductance, calculate the L over R fraction, and that will tell you how much time you need to wait for the current to drop significantly.